All right. In this video, I'm going to be talking about tangent planes and normal lines. And now I am kind of assuming that you were here on the day when I did the lecture and I kind of showed you the general form. I'm just going to be working some examples here. I might mix in some other stuff from, this is the second unit of multivariable calculus where we're taking partial derivatives. We might look at some extrema depending on how far I get in this video. This is mostly I've got a few people absent today, and so I'm just recording this video for y'all, so you know what the examples look like. All right, so the first one, I'm going to take the tangent plane to f of x and y is equal to log of x over e to the y at the point where x is e, y is 1, and z is 1 over e. So, what is that going to look like? Well, I've got a point, I need kind of like, a gradient, basically, and then I'm going to write down the equation of the tangent plane. Well, the gradient of f is equal to, the partial with respect to x. Well, this e to the y in the denominator is just like a constant with respect to x. So I'll have the derivative of log x is 1 over x, and then the e to the y will remain the same. Now when I'm taking with respect to y, I'll have that log x remaining the same. But this is really e to the negative y, so it'll be negative log x e to the negative y. Okay. Now, at the point where x is e and y is 1, gradient of f at the point where x is e and y is 1 will be, what is it going to be? 1 over e squared. And negative 1 over e. Is that right? All right. Now, remember that you can kind of just do point normal. For this, you can just do z minus 1 over e equals the gradient, or the partial with respect to x at the point you're interested in, times x minus e plus the partial with respect to y minus 1. And then that's an equation for a tangent plane. All right, now we've got tangent plane to kind of an implicit relationship. Z squared minus 2x squared minus 2y squared equals 12 at the point where x is 1, y is negative 1, and z is 4. I'm going to try to produce a rendering of this surface, and we'll see what I can get. I'm going to pause and then come back with. All right, there we go. It's a two-sheeted hyperboloid. So, it's kind of like the hyperbola in regular XY space, except it's a solid. It kind of looks like, what is that? An hourglass, right? Yes. Could maybe drop some sand out of this one into that one, All right, well, it's good to know what these things look like, but you don't need to just be able to visualize that based on the implicit equation. That's not something that we need for this class. And really, I don't think anybody needs that anymore now that we've got stuff like Wolfram Alpha and, other 3D plotters. All right, so I've got this implicitly defined surface, and I'm interested in writing down an equation for a tangent plane truth. So I'm going to get some partials. What we really have is if we have a function of x, y, and z set equal to 0, and we take the partials of that function. So, and that's definitely what you would see in the Larson textbook also. So it's going to be, z squared minus 2x squared minus 2y squared minus 12. And this is a function of 3 variables, and meaning that we are looking at its level curve, really its level surface, at f equals 0. So the partial of f with respect to x is looking like negative 4x. Okay. Partial f with respect to y is, what's it going to be, negative 4y. And partial of f with respect to z is going to be, 2z. Okay, so I kind of go in and I, plug in the point. So at the point I'm interested in, the partial of f with respect to x is negative 4 times 1 is negative 4. Partial of f with respect to y is negative 4 times negative 1 is positive 4. Partial with respect to z is 2 times 4 is 8. Meaning that what we can do is we can just kind of do, I'll set up the skeleton, because I don't think I actually did it. I wrote it down over there on the blackboards. Of course, you can't see if you're watching this video at home because you're absent. But the equation is partial f with respect to x times x minus x naught, and so on equals 0. So that's what I'm going to do. So I'm going to say that negative 4 times x minus 1 plus 4 times y plus 1 plus 8 times z minus 4 is all equal to 0. And that's how we do it. Okay, so the tangent plane should be very, very friendly to us. Okay, now I've got a normal line question. And all right, so let's see, x, y, z equals 12. Let's get a little rendering of this. All right, so yeah, there you go. It is not exactly the surface that you would expect. Now, keep in mind, I believe that we are only looking at, 1 octant, right? So it's 1/8 of space. Here's the thing about there's going to be like kind of 4 quadrants, and there's above and below the origins, right?
It looks like the altitude, but it's just in the top left corner, so it's perspective.
It's in the what?
It is in the center. Look, it's in the.
The corner is the center, correct?
No, I think the center is the center.
Yes, I stand corrected. We are not looking at 1 octant. What we are looking at is a thing that does have some symmetry, and there's 4 pieces of it, and that one right over here that looks different from the rest, like we're just looking at it straight on, yeah. We're just looking at this one straight on, we're looking at this one from backwards, and this one kind of from the side, and this one from above. So that's what that looks like. And a normal line, okay, if you can envision the tangent plane to this thing, a normal line is a line that lies perpendicular to that tangent plane. So let's just go ahead and write ourselves down a normal line, because this is not... Yeah, as far as categorically classified, yes, that would make sense. All right, so what we're going to need is a gradient. Okay? What we're going to do is we're going to find the, maybe since it's an implicit relation, I'll set it equal to 0 and write, f of x, y, and z is x, y, z minus 12. What I'll do is I will find the partials here. So partial of x with f with respect to x is going to be yz. Partial of f with respect to y is going to be xz, and partial of f with respect to z is going to be xy. That was very friendly. I like that. All right. So at the point we're interested in, yz is going to be 6, xz is going to be negative 6, and xy is going to be negative 4. Okay. So the gradient of f at the point 2, negative 3 is going to be the vector 6, negative 6, and negative 4. And because of the way the gradient sits orthogonal to the level sets of a function, well, this is going to be our trajectory of our normal line. So it's going to sit normal to the actual surface. So I've got a point, I've got a normal, and I'm looking for a line. We can parameterize this very easily. Now, some people might ask me for symmetric equations. I'm just not a fan of symmetric equations myself. I prefer a vector equation for a line in space. So that's what I'm going to do. I'm going to write it down as a vector. Okay. That's the easiest way to think about a line. It is the most useful, at least that I know. I'm not really sure what the symmetric equations are good for. I guess it'd be good for finding the intercepts. But, you know, anyway, so the line, the normal line, is going to be the vector 2 plus 6t, negative 2 minus 6t, and negative 3 minus 4t. We've done this a few times in the past, but I have realized that there was not ever a day where I just sat y'all down. I was like, here's how you write the equations of lines in space and planes in space. I should have done it, but my excuse this year was that I think I was out sick during the time of the year where I should have been doing that. Then I got back and I felt like we should be doing linear algebra. We should be really like knee deep in it. I've been gone for 2 weeks and been doing basically nothing. So I think that will probably be all for tangent planes and normal lines. And then what I'm going to do is, you know, we're taking B lunch today, so probably in the second half I'm going to do a little bit of work on extrema of a function of several variables, which is actually going to be, it's very procedural, and, you know, it'll not be, you know, that, I'll be like, oh, this is like the second derivative test, but just more. And it won't be your favorite thing, won't be your least favorite thing either. All right, so that'll be all.